So we're going to break the talk down into 3 sections. We're going to start off with a very, very brief overview of how to draw stuff in Qt3D and custom materials. And the main bulk of the talk, we're then going to talk about physically based rendering and some of the theory behind that. I apologize now, there will be some equations. Try not to be scared by them. It all boils down to be something quite simple at the end of the day, so just bear with me. And then right at the end, we'll show how we can implement this inside of Qt3D and also some tools that can help us generate the textures that feed this rendering method. So without further ado, if you want to draw something in Qt3D, we have this object type called entity. Okay, an entity, for those of you who don't know Qt3D, is basically just an empty building block. It doesn't do anything by itself. To give an entity some form of behavior, i.e. something that you might see rendered, then we have to attach some components to it. We're not going to go into the full entity component system framework today, just to give you a very brief taste of it. So for example, to render a donut-looking example, which I'll show in a second, we would need to add a piece of geometry to our entity. This is our torus mesh, and we also need a material, which gives us our surface appearance. And you can see in that example there, we've specified some extra textures, the diffuse map, which gives it a basic color, a normal map, which lets it know where there's extra lumps and bumps, even though we don't have real geometry for that. And finally, a specular texture, which says which areas are shiny and which other areas are not as shiny. Okay, so if we do something like that, we may end up with an example that looks something like this. Okay, so we have a nice shiny donut. So that code sample gives that kind of thing. Yep, very, very simple stuff. This is using like an old traditional Phong lighting model with normal mapping applied on top. So far, so good. It's using a built-in material that comes with Qt3D called normal diffuse specular map material. Just rolls off the tongue, I know. It's also very easy to add your own custom materials. So to do that, we would need to specify a material element looking something like this. So a material, the important thing it has is it has an effect. An effect contains, eventually right down at the bottom level, references to the shader source code that actually gets executed on your GPU. We can also specify other parameters inside of our material, and we can use property bindings from QML to feed these parameters all the way down into the GPU as uniform variables. If you don't know what I'm talking about with uniforms, this is just a way we can parameterize our shader programs and easily tweak them without having to spend a lot of time recompiling them. So, knowing that we can have built-in materials and custom materials in Qt3D, let's see what we can do along the lines of actually getting some physics-based rendering materials in there. Now, first of all, why do we even want to do this? Well, traditional lighting models, like the donut example I showed you a minute ago, they tend to mix up the lighting properties along with the material properties. The two are very tightly coupled together in non-intuitive ways. So what we'd like to do is somehow separate those two things so we can have a material that has very reliable properties that we can specify in units that we can relate to, and that can be then used in any lighting situation. Okay, with ad hoc methods, you end up with lots of nasty hacks to get things looking right in different situations. If you have a material that looks nice under a bright light, then it looks okay. If you then take that same material and try to put it into a darker scene, all of a sudden you'll find your material doesn't look right, and then you'll tweak all the parameters of it, go back to your light scene, and say, oh no, now it's broken over there. It's very hard to get right. And this leads to all sorts of nasty hacks and things like using negative lights in the bright scenes to compensate for the things you need to make work in the dark scenes. It's just horrible, and people spend hours tweaking these things, and artists pull their hair out, and nobody's happy. So that's the motivation. So PBR tries to address some of these things. There's also some other nice features we'd like to get into a newer lighting model, so things like energy conservation. Okay, if we have a light source shining on an object, it stands to reason that object cannot reflect more light than is hitting it in the first place, if we ignore things that are emitters like light bulbs. So we want energy conservation. It would also be nice if we can use some actual physics to perhaps model how light interacts with matter. So that's where the name came from, physics-based rendering. if it can be controlled by more physical parameters rather than made up things, that would also be nice as well, because people can relate to these and we can write tools and parameterize our shaders this way, and artists are much more happy to control these things knowing they're going to get predictable results. And very importantly, it does decouple the lighting and the material properties. So we don't need any of these nasty hacks anymore. Okay, so first of all, we need to worry about what is light. Well, as you may remember from high school physics, light can often be treated as either a particle, a photon, or as waves. Now, for our particular purposes here today, we're going to think of light as photons, particles of light. Now, the one tip of the hat we need to make towards wave notion of light is that of energy. The wavelength is still important. And down the bottom there, you can see that we can relate the wavelength the wavelength lambda with the frequency nu with the speed of light, which is c. Now, knowing what the frequency nu is, we can work out the energy of a piece of light, a photon, by multiplying it by Planck's constant h. This is, again, all high school physics stuff. Now, once we know the energy, we can then work out the power in watts over time by taking the derivative of that with respect to time. So that's what we're going to call phi here. That's a radiant flux. Now, there's another quantity called the irradiance we need to worry about, which, think about that as the flux of, the radiant flux going through a unit area. Okay, so this is watts per meter squared. Now think about this as sunlight shining on a meter square of pavement outside. On a bright sunny day on Earth, that's around about 1,000 watts, I believe, per square meter. So that's quite a lot of energy coming from the sun. So that's a measure of light flowing onto a surface. We then have the intensity. So if we consider a non-directional light source, so imagine we have a light bulb, which is in our scene, and then we're interested in what is the radiant flux per solid angle. The solid angle is just like a cone emanating from every point on that light source. And if we integrate over all angles, then we get the total radiant flux for that light source. And that's measured in watts per steradian. There we go. Now we can relate the radiance to another property called intensity. If we consider that we have a light source, which is a point, and then if we imagine we have concentric spherical shells around it, as we get further and further away with these shells, the surface area of these shells is getting bigger as 1 over r squared. So it's the r squared that relates intensity versus the irradiance. Now, the irradiance and the intensity gets us almost to where we want to be, but we need to consider not just area and not just direction. We need to consider both of these things. So we also need to take care of the fact that if we have a surface, our unit area, and we have a light shining down onto it, there's an angle that's between those, okay? And there's a cos theta factor we need to take care of because the light is not directly above, it's to the side, So we have a projected area to worry about. This is where this dA proj comes in. So this is the radiance, and it's measured in watts per meter squared per steradian. So think of this as the amount of light coming from a light source hitting our surface. So radiance is an important quantity. Now, so far we've been dealing with purely physical values, but with rendering we also need to worry about perception. There's another field called photometry, which maps this radiometry onto the sensitivity of the human eye. And then colorimetry modulates that by the spectral response of the human eye. Now, very lucky for us graphics engineers, the human eye is incredibly lossy. Okay, you can take many, many different spectral distributions, and we will interpret them with our puny little meat bag eyeballs as being exactly the same color. We are terrible at resolving color. But the good news is it becomes much cheaper for us, because now we can just boil down an entire spectral distribution to an RGB triplet. So we only have to do this for an RGB triplet, not the entire continuous spectrum. That would be far too expensive. If you're doing full-on physics simulations, that's what you have to do. Okay, so we know about, where have I gone? Have I gone too far? Radiance. No, that's fine, sorry. So given the irradiance from a light source falling on a surface, we need to worry about how much irradiance we are getting back, which actually ends up in our detector. Now, there's a function relating these two things called the bidirectional reflectance distribution function. Here we've called that f, and it's a function of two variables. It's a function of the view direction, v. So if you imagine I am the piece of surface area, okay, you guys are the viewer, then the v vector is the vector from me to you. The other important vector is the light direction. So up here we have a light shining down on me, so the L vector is the vector from me to the light. They're the two important quantities. So given those two things and some properties about the surface, then this bidirectional distribution function will tell us how much light you actually see reflecting off me. Some more good news. If we're dealing with point light sources or other non-area lights, then we can get rid of all these nasty differentials and integrals and things, because the solid angle actually becomes zero. We're just dealing with discrete points. And in which case, we can just end up using discrete summations rather than integrals and things. This cos theta I factor on the bottom there, this is the cos theta to take into account how much light is actually falling on our surface with the angle that we need to consider. And that can be calculated conveniently as L dot n, where n is the normal vector pointing away from the surface that we're trying to shade. Now, if we rearrange this and sum over many lights, we get a very important equation called the shading equation. Now, it looks scary, but it's actually pretty simple. So the term on the very far right-hand side, this EL, that's the irradiance coming from a given light source. We multiply that by cos theta to reduce down the projected area. And then we're just doing a component-wise multiplication, that funny circle symbol with a cross in the middle, and we're multiplying that component-wise with this BRDF function, which, as we said, is a function of the light vector and the view vector out to you guys. And then we simply sum that up for all of the light sources, and that's the color that we need to shade that particular fragment we're trying to worry about. So the BRDF, what the heck is this thing? Well, conceptually, the BRDF, if we have a surface area we're trying to light, then if we have a certain amount of light shining on it, it says how much light reflects off it in any given direction. Or equivalently, if you have a view vector in a given direction, what contributions come from that from light sources in different directions. So you can work it out either way. Now, isotropic BRDFs are only concerned about the relative angle between the L and the V vectors. Okay? Non-isotropic materials, you can't make that assumption. So things like brushed aluminium. So we're now at the point where we need to just specify this f function, right? Okay? Let's see how we can go about that. So now we need to start considering something about physics and how light interacts with matter. And there's three main ways in which light interacts with matter. There's scattering. So if light shines onto something and it gets scattered, it basically just changes the direction of the light. It's not changing how much light there is. Very important. The second method is absorption. So light hits a surface, some light is absorbed, and some is reflected or refracted. So that actually reduces the amount of light that we're dealing with in our system. Some light is lost, some energy is lost. And thirdly, there's emission. We're going to completely ignore emission here, apart from worrying about our initial light source in the first place. So how does scattering versus absorption manifest itself? Well, this nice diagram here tries to illustrate that. So on the x-axis, we have increasing levels of scattering. So we start off with a glass of pure water, and you notice you can see the barcode situated behind it through the water. Yes, it's been distorted by refraction, but you can still see it. If we increase the amount of scattering, we lose more and more information until we end up with full fat milk on the very right-hand side there. We've got no information making it through from behind our cup. And up the y-axis, we have increasing levels of absorption. So you can see there, absorption does not lose information, but it does lose energy. And it gets a color tint because we're absorbing some frequencies of light more than others. So this is what gives things color. Scattering destroys information, scatters it around, but doesn't lose energy. That's why the milk is still very white and bright. But absorption does it the other way. So let's consider ray optics. Now, if we have a material which is optically smooth, i.e. the imperfections are less than the size of the wavelength of visible light, which we're worried about, we can describe the optical properties of that surface or material by its index of refraction, eta. Now, when we have an optical discontinuity, i.e. when we transition from one type of material to another, i.e. from air to some other material, such as metal or wood, then there's an optical discontinuity. The indice of refraction changes. Now, we have various things that happen at that boundary. Some light can be reflected, and some light can be refracted, and then undergo further scattering events. Now, different material types behave in different ways. Metals typically undergo surface scattering only. They have a sea of free electrons inside the body of the material, which very, very quickly absorbs any light that does manage to penetrate. So for all intents and purposes, metals undergo surface scattering only, not absorption. Dielectrics, or insulators, on the other hand, the light penetrates and then undergoes multiple scattering and absorption events. So you can see here we've got the arrow coming in, and for the arrows that penetrate the surface, they're being bumped around and scattered many, many times. They're changing color because some light is being absorbed, and then some of them will actually manage to escape again. This is what gives materials their more diffuse color appearance. And finally, there's semiconductors, which we're going to ignore because we don't tend to render many semiconductors in real time. So we have metals and we have dielectrics. It seems perfectly reasonable that we should have a term for each of those things inside of our bidirectional reflectance distribution function. And we're going to call those specular and diffuse. We now need to worry about something called the Fresnel reflectance effect. Now this again assumes an optically smooth surface, and basically what it is assuming that the amount of light that gets reflected is dependent upon the angle of incidence of that light ray. Now you can see this in everyday life. For example, if you're standing by the side of a lake on a still day, then the surface of the lake acts like a mirror, and you can see the sky and the trees reflected in it. If you were then lucky enough to go up in a helicopter ride above the lake and look straight down, then you can actually see to the bottom of the lake. It's not a mirror any longer. And that's entirely due to the Fresnel reflectance effect. Now this is described fully by the Fresnel equations. Unfortunately, these are very, very complicated, and in the general case, they're actually complex. Now, this has traditionally been too expensive to do in real-time rendering, but some engines nowadays are actually starting to implement the full Fresnel equations in their shaders. However, for our purposes, we're going to use an approximation called the Schlick approximation. But before we get onto that, let's see an example of how this looks. So on the bottom there, on the x-axis, we have the angle of incidence of our light. And then on the y-axis, we can see the amount of light being reflected. So you can see as we start off at an orthogonal angle, the light is shining down, we have no reflection. As the angle increases and increases, then eventually at some point it rapidly changes and goes up to 1 to be almost fully reflective. And different materials have different values at 0 degrees of incidence, so when it's orthogonal. So dielectrics tend to be having very low values of Fresnel reflectance at 0 angles, and metals tend to have much higher ones. And some metals, such as the curves on there for copper and aluminium, are actually colored because the Fresnel reflectance varies differently for each of the 3 wavelengths that we're considering. So we're going to use Schlick's approximation. Okay, this is a pretty good approximation to the full Fresnel equations. It gives the right kind of behavior. It loses some accuracy for some materials, but for the most part, it's perfectly fine for real-time use. The nice thing about it is it's very nicely parameterized. We can specify the Fresnel reflectance at an orthogonal angle at 0 degrees, and from that, we can then calculate the Fresnel reflectance amount at any angle. So we specify this RF of 0 degrees as an RGB triplet, often specified in the sRGB color space, so we have more precision at the lower end. And typical values are metals tend to be greater than roughly 0.5. Dielectrics are around 0.04 to 0.08, thereabouts. Gemstones and semiconductors are somewhere in between. And there's some sample values from you out of the real-time rendering book. So gold, you can see there, is actually very, very strongly colored. It has hardly any value in the green channel. Whereas dielectrics tend to be monochromatic. Right. So now we need to worry about body reflectance. So we've understand how much light gets reflected from the surface. Now let's worry about the light that penetrates the surface and what happens to that. So this is the diffuse term. Some insulators are very, very homogeneous. Okay, if you have pure water, that's an insulator. Believe it or not, it's actually the impurities in water that make it a conductor. So if it's completely homogeneous, such as water or very high quality glass or crystal, these things tend to be transparent because we don't have any optical discontinuities. However, most insulators, things we're more familiar with, like wood and plastic and soil, skin, they have lots and lots of optical discontinuities. So this is where we change from one material to another, or there's like a macroscopic break in the material. Now in that case, we have lots and lots of scattering going on because we have lots and lots of optical discontinuities. So the picture there of the beer is there for two reasons. I mean, one, I like beer, and the second reason is to try and understand the difference between optical discontinuities and not having optical discontinuities. So if you look at the main liquid of the beer, it's strongly colored. What does that tell us? That tells us there's lots of absorption going on. However, we can still see through it, so that means that there's no optical discontinuities, or very few optical discontinuities. However, the head of the beer on top is very bright, so we know there's not much absorption going on, but we can't see through it. Yeah, the information is destroyed by the scattering. And the reason for that is we have lots and lots of optical discontinuities. The bubbles in the head of the beer are made up of beer liquid, followed by the air gap, followed by more beer liquid, and so on and so forth. Now, every time we go through one of those little bubbles, the light gets scattered, and we lose information. But it's still bright. The light is not passing through much actual liquid of the beer, so it stays the same sort of color. It just becomes white because we can't see through it. So yeah, the body reflectance, we tend to represent that with a simple term in our BRDF, and by far the most common term to use is the good old Lambertian BRDF function. This basically just says that for light shining on a surface, the light is then scattered equally in all directions over that hemisphere. So very, very simple. There are other diffuse BRDF terms that are in use. In particular, there's one made by Disney, which they've used in their films for the last 10, 15, 20 years. That's now starting to feed into real-time rendering as well. We're now reaching the level of hardware where that's possible to do. So far we've considered Fresnel reflectance and the diffuse term. Now we need to start worrying about the specular term a bit more. So this is the light that's been reflected from the surface. How can we model this? Well, this is where we need to introduce something called Microfacet Theory. Sounds scary, but it's not too bad. Now, surfaces have multiple scales of features. We have the macroscopic features, which is what we're normally used to. We model a surface, we specify some normal vectors in our modeling program, and that's what we use for our lighting models. Everyone's happy. There's also the nanoscale. This is defined typically to be surface features less than the wavelength of visible light. We're going to completely ignore this for now. There's some research going on that says this may actually be important in terms of worrying about things like diffraction effects and how that affects the rendered results, but we're going to ignore that for today. And then in between, there's the microgeometry. Now, this is the scalar geometry where the imperfections in the surface are much larger than the wavelength of visible light. However, they're much smaller than the typical size of a pixel we're trying to render on the screen. So what can we do about that? It's important because it affects the light, but we can't take care of it exactly. So we're going to do it stochastically. We're going to use probability. Then what we do is we basically say inside of our pixel there's a whole bunch of little surfaces, each of which we're going to treat as a perfect Fresnel mirror. Now the reflection vector R can be calculated, as you can see from that equation there. We can't do that for every little point inside of our pixel. So we're going to treat it stochastically, and we're going to use something called the normal distribution function to basically say how many of these little mirrors covered by our pixel are pointing in the right direction that we can actually see the reflected light. So this is going to be affected by things like the roughness. So we've got two photographs of similarly shaped objects there. They both share the same kind of macroscopic shape and normal vectors, but the reflections on them look very different. And the difference is caused by the microscopic structure at the surface. So for the top object, it's quite smooth. The surface, the microfacets are all pointing in roughly the same direction as the macroscopic normal vector. And for the bottom object, the microfacet normals are much more higgledy-piggledy. They have a much wider distribution. So roughness is something we might want to consider as one of our control properties. Now most materials have a continuous normal distribution function with a strong peak aligned with that macroscopic surface normal. Some of them don't, in which case you might want to have a different NDF for rendering special things like the moon, which has very strong retro reflection. But for now, we're not going to worry too much about that. So the strength of this peak is a measure of the smoothness or roughness of the surface. So the rougher the surface, the more the microfacets are spread out at different angles. And the more blurry our reflection becomes. Again, most materials are isotropic, but some of them, like brushed steel, brushed aluminium, have very, very strong directionality. And in that case, the NDF is not isotropic. So if we have a bunch of these microfacets, these little tiny mirrors underneath our 1 pixel, which ones should we care about? Well, we only care about those microfacets where the normal vector is halfway in between the light vector and the view vector, because it's those ones that are going to be reflected off into the detector, i.e. your eyeball or our virtual camera. Something else we should probably care about is shadowing and masking. So now we're down at this microscopic level. You can see on the left image there we have light rays coming in, and because of this microscopic structure, some of them are actually getting occluded. Yep, they're being shadowed. So it would be nice in our BRDF term if we had some way of accounting for some light that cannot actually see the normal, the correctly oriented microfacets with their normal vector pointing in the right direction. So we need to reduce that somehow. Same thing for the light that actually has been reflected. Some of it may hit some other hills on the way out and be occluded that way. And then finally, we should probably worry about multiple bounces of light at this microscopic scale, but here and in current cutting edge shaders, this is still ignored. Now in general, the specular BRDF term has been derived as this by some very clever people, and there's a few things we can look at here. So this term on the top here, this D term, this is our normal distribution function. So we provide a function that says how are our microfacets pointing in different directions for our surface. And then we say of that fraction, which fraction of those microfacets are actually visible according to our geometric properties. like how many of them are shadowed, how many of them are hitting other bits of geometry on the way out after they've been reflected. That's the geometric term. And then finally, we have the Fresnel term, which says how much light is actually reflected in the first place. And all the stuff on the bottom is just normalization coefficients to make things work and balance properly. So now, if we take our general purpose specular BRDF, and we now try to plug in our diffuse contribution as well. So we're going to take here our good old Lambert diffuse term plus the traditional Phong specular term, which you may well be familiar with from older lighting models. Then we can basically write it down like this. So we have the diffuse term on the left there divided by pi plus the specular coefficient, and then that's multiplied by this m plus 8 over 8 pi thing multiplied by the cos theta factor. Now this m parameter is a measure of the smoothness, or equivalently the roughness, of our surface. And then down the bottom there we've just included the Fresnel term on the specular part there. And if we compare that to our general purpose microfacet specular BRDF, we can actually see that the Phong plus diffuse term there reduces down to having our G function, our geometric function, being set to 1, i.e. we're completely ignoring shadowing and masking. And the normal distribution function, D, is actually coming out at that specular term that we had there, taking away the Fresnel part. So if we feed all of that back into our original shading equation, then we end up with this here, and after a bit of simplification, we end up with that term on the bottom. And that's what we need to implement in our shaders. So if we look at that, basically all we're doing is we're working out our BRDF function for our particular point on our surface, multiplying that component-wise by the irradiance from the light source, multiplied by the cos theta attenuation factor, sum that up over multiple light sources. That's the color of our final pixel. Yep. So we've considered quite a few things on the way, but at the end, this is the equation we need to code up. It's pretty simple. Not quite done yet, though. We also need to worry about energy conservation. Now, if you think, if we have a surface with light shining on it, then some light gets reflected. We know that from the Fresnel term. Some light then transmits and undergoes further scattering. So it's the specular term that gets first dibs on the light. So we can work out how much light is available for the diffuse reflection by doing 1 minus the specular contribution. Yep, we can't make more energy than what is going into the system. So in summary, the PBR family of techniques basically tries to consider all these things. So we need to have a BRDF function, and the BRDF describes how light is reflected from the surface, giving incoming light. So knowing the light direction and the view direction, feed that into our BRDF, sum them up with the number of lights, and we're done. Now the BRDF is broken down into two things, the diffuse and the specular terms. And the diffuse is often just this simple Lambertian term, very, very easy to write and very quick to evaluate. The specular BRDF is typically based on Microfacet Theory, and it consists of the normal distribution function, the geometric function, and the Fresnel Reflectance. And then right at the end, we have energy conservation coming in. Right, so now what can we do with PBR along with Q3D? Well, if we start simple, we're going to just worry about point lights to start with, and we're going to have a material where its properties are constant across the entire surface. And we're going to express those material properties in terms of those 4 quantities down the bottom. So we have the albedo. This is like the diffuse color of the material. We have a roughness parameter, which says how shiny or rough the surface is and leads to the type of specular reflection that we see. There's the F0 color. This is the color of the material when you're looking at it straight down, okay, from the Fresnel reflectance equation. Remember that graph? And then finally, how metallic our surface is. Is it metallic, or is it dielectric, or is it somewhere in between due to impurities? So with those 4 things, we can actually write a shader that does all of our PBR calculations. So if I find the example and fire that up, there we go. So we have the Suzanne model from Blender, and you can see in the background there I've got some blue points which are light sources, and as we move around we can see the highlights on the monkey head changing and moving around. And then on the left here we've got different controls we can change. So we can change the roughness level, and that changes the size and the spread of our highlights. Okay, so now we've got something that's more rough. We can move it back down to be more shiny. And you can change the F0 color to make it look more like different materials. So we can set that to yellow, for example. And then if we increase the metalness up to there, say, and the roughness to there, we can have something that looks a bit more like gold. Yep. So quite easy to change these parameters to get different types of materials by changing the roughness, the F0 color, albedo, and metalness. Now if we look at the shaders for this, it's again pretty simple. So in our main function of our fragment shader, this gets executed once per fragment for those of you that aren't familiar with OpenGL and shaders. We're basically trying to work out the color of each particular pixel that we're rendering. So we start off with a color, which we're calling C linear, initialized to 0, and then we're iterating over each of the lights in our scene. For each of them, we're adding on the contribution from this PBR model function, which we'll look at in a second, and then right at the end, we're just applying gamma correction before outputting it for display on the screen. So inside of this PBR model function is where we do the work. And you can see in here we're just working out some useful quantities like the L vector, the direction to our light, the V vector, which is our view vector from the surface to the observer, and the half vector, which is the one we need to feed into the normal distribution function. We work out some useful dot products between those things, and then we calculate our diffuse model. This is just our simple Lambert term, nothing interesting to see in there. And then there's the specular model, which is just here. And then you can see from here, we're just calling a function to calculate the Fresnel factor using that Schlick approximation. We're working out our normal distribution function, D, which is nothing particularly exciting. It's using that m plus 8 over 8 pi thing that we saw earlier multiplied by the cos theta factor. And then the geometric model, this is the one that we found out was just unity, so literally that just returns 1 here. Of course, if we are optimizing this, we'd just remove that. And then we multiply these things together, so we've got our Fresnel times the normal distribution function times the geometric factor, divide by the coefficients we saw to normalize it, and that's our specular contribution. So we now have diffuse and we have specular. We combine these to make sure we have energy conservation by doing the 1 minus specular thing. And we're multiplying our BRDF function by our light intensity and our cos theta factor, and we're done. Yep, so it literally is a direct translation of the equation we saw on the slide into GLSL shader code. So, what can we do further? Well, it's nice if we can have different material properties across our surface. So to do that, a typical approach is we encode our material properties into textures, and then we apply those that we can sample from at each point across our surface. So in this case, we're going to keep it simple and still use point lights, but now we get our data from textures instead of hardwiring fixed numbers. So here we have a cube. If I zoom in a bit, so you can see we've got this pattern going across it. Oh, I've gone zoom too far. And then as we move around, we can see the reflection is affected differently by the different levels of roughness on that surface there. Yeah. And we're getting the elongated highlights which come from the Fresnel effect. Right. Sorry, that comes from the half angle consideration, not Fresnel. Right, so typically with those textures, we would specify both the albedo and the F0 color in a single texture called the base color. which we extract those from, and they're typically in the sRGB color space. Then we have a roughness map, which basically says which areas of the surface are rough and which are smooth, and we have a metallic map, which says which areas are metallic and which ones are dielectric, or in between. And then if we go even further, then we can actually start doing more clever things rather than just using point lights. Now, if we have another texture in the form of a cube map, then what we can do is for each point on our surface, from our camera, we can shine a vector at it and reflect that from the surface out into our cube map environment. And then from that, we can then treat that as the light source for that particular fragment. Now, if we do that, and we have to take care of worrying about convolve this for all the different angles it can see, then we end up with some nice lighting effects. So if I fire this one up, where are we? This one. Okay, so now here we have another model that's been textured with these shaders containing like the base color, the metallic map, the roughness map, etc. But now the reflection is coming from the environment. So rather than looking like it has harsh point lights everywhere, we can see a much smoother variation of light across the surface. Okay, we're not actually rendering the environment here, we're just using it as the light sources. Okay, so now I'll just show another example which shows it along with the environment so you can get a better idea of what's going on. So if I just brighten this up a bit by increasing the exposure, then you see we've got some nice rocks, okay, with some water in the crevices there. Let me just zoom in a bit. So again, what we're doing here is just specifying those same textures with different input data, and we've got a completely different looking surface, but because it all follows the same physical principles, we don't need to change the shader code at all. Okay, it's just feeding in different input data. So we've got some areas that are rough, some areas that are smooth. We've got some areas that have different heights. So what we're actually doing in here as well is we're building on top of our basic PBR shader, and we're applying something called parallax mapping. So parallax mapping is a bit like normal mapping, where you fool the lighting equations by perturbing the normal vector a little bit. We're also taking advantage of the information stored in another texture called the height map. So by doing that, we can offset the texture coordinates in a very special way, such that it looks like this perfectly flat surface. Actually, this is just a cube, okay? There's no actual real lumps and bumps on here. If we perturb the texture coordinates, it fools the eye and the calculations into actually occluding other bits of geometry that isn't actually really there. So if I switch over to that mode and bump this up a little bit, then you can see we can actually control the scaling we apply to that on the fly. Yep, so now you've got very nicely lit and shaded stones behaving as you would expect optically, and they actually look like there's more geometry there thanks to this parallax mapping. So this is actually not that difficult to do. It's a few lines of shader code in a function. If you're interested in details, come grab me afterwards. And then if we want to change this cube how it looks, I can just load up a different material. So this one is using the rock textures. If I load up that checkerboard pattern again, then we can see now we've got a completely different appearance. The shader is exactly the same. All we're doing is changing the input data. Okay. So how on earth do we make these things? These textures? Well, for doing the convolution of the environment maps for these things to worry about the diffuse lighting term and also the different levels of specular reflection we get for different levels of roughness, then you have to pre-convolve these offline. You can try to do it online using importance sampling, but that gets more expensive. So if you want to take the pre-convolution step, there's a handy little tool called LIS, which you can download and buy for about, I don't know, I think it's about $80 or something like that. But you basically feed it a cube map and set the various roughness levels you're interested in, and it will spit out a whole series of bitmaps in a compressed texture for you. You can then sample from for your different levels of roughness and reflections. Very, very handy tool. It's pretty quick as well because it does all the convolution on the GPU. Yep, and then we can go even further and we can use high definition rendering. So that last example I just showed is doing the calculations in the full floating point number space, not just the 0 to 1 range, like low definition rendering. And then at the end, we just have to apply tone mapping to scale our values from 0 to infinity back down to 0 to 1 so they can be displayed on the monitor. And there's a whole bunch of different tone mapping functions you can apply. I'm just using a very simple one here, but there's some very nice ones like the filmic tone mapping used in the Naughty Dog games, for example. There's a whole bunch of them. How do we actually create the textures that feed into our PBR shaders? There's some very, very nice tools from a company called Algorithmic. Their tools are all written in Qt, which is nice. And there's two of them. There's Substance Designer, which allows you to basically generate a graph that generates you materials. Okay, it's a way of procedurally generating these textures. And you can then export them from these tools, load it straight into our PBR shaders, and you're done. Substance Painter takes those materials that you've generated and allows you to paint with them in 3D. It's basically like Photoshop for 3D. And then once you've done that, again, you can import that back into Substance Designer, export them as the textures, and use them in your application. So doing that is how I made that traffic cone. So you can texture different areas with different materials, and then you can apply effects like adding on mud and rust and things like that. Very, very nice tools. Highly recommend you go take a look at those. So there's a screenshot of the Substance Designer, and you can see at the top there we've got the graph, which eventually generates the checkerboard pattern that we just showed in the last example. Very, very nice and easy to use. And there's a screenshot of Substance Painter. So yep. Down the bottom you have your selection of materials, and you can have layers and things that you can set up at the top right here, paint on them. Very, very nice. Okay, so we've seen how we can go from our good old-fashioned traditional ad hoc lighting models, and we can consider the things we need to worry about with physics-based rendering. And we saw right at the very start how easy it is to make a custom material in Qt3D. You just have a material where you specify an effect with your custom shaders and any uniforms you want to set. Been through all the PBR theory, and then we've just shown at the end a few examples and some helpful tools to generate the assets for it. And that's it. Thank you very much. Any questions? There's a microphone coming around for questions.
It's a short one, only that, are you going to have the presentation available on internet?
Yes, yeah, we'll put the slides up online after this.
Okay,
yeah.
Thank you.
Hi, you mentioned earlier about this being much better in different lighting conditions. Would it be actually possible for you to demonstrate that?
Let me see on this laptop. Parallax. Run. Yeah. There is a button here for change the environment map, but I think it's broken. So this is like a park scene in daylight where you can change the exposure. So if I bump that up so it's more like a bright day, it looks quite natural in that fitting. If I dumb it down to something more like an evening time scene, it still looks more natural. It's a bit too dark for this screen. If you come find me afterwards, I'll get it to load up a separate environment map. I just need to hack a bit of code to make it work, because that button doesn't work at the moment. But it does reflect the lighting environment very, very well and just look like it should be in that scene. But yeah, come find me afterwards and I'll show you it.
Thanks. I've used subsurface scattering for skin, and I was wondering if you could give an example of what other considerations you use to maybe do a skin shader.
Yep, for subsurface scattering, it's based on the same principles. It's essentially changing the diffuse term, because what you're doing with subsurface scattering is you're saying the light shining and hitting a surface, it bounces around a lot because you've got many, many layers of skin, and then pops out again. But where it pops out might be in a different pixel. So essentially with a subsurface scattering shader, you're having to worry about the light hitting from several other pixels. So it's basically an approximation that tries to work that out. So all the subsurface scattering shader does is basically saying the light that comes out of this pixel may have actually entered from a different pixel elsewhere. So I don't have any examples of that up here at the moment, but there are examples you can find on the internet of subsurface scattering quite easily.
Thanks.
Dr. Hammer, is there any plan for you to provide like a shading library along with Qt3D?
Yes, I'm hoping to get the PBR stuff upstreamed, hopefully for 5.9.
5.9?
Hopefully, yes. In which case you'll just be able to pick these up and use them as a built-in shader.
Yes, it's very handy.
Yeah, and then all you need to do is worry about providing the textures.
Okay, thanks.
But that's the tricky bit. Anything else?
I'm not sure if my questions are related to this topic. So compared to the traditional OpenGL pipeline, what's the advantage of Qt3D? Like, do we still need to like build all the cameras, all the?
Okay, right, yeah. So Qt3D in general is built on top of Qt3D, on top of OpenGL. So we try to expose as much of the functionality of OpenGL as possible. The nice advantage of Qt3D is you don't need to worry about all the low-level plumbing to make that happen. You can just say in QML, I want a camera. If I fire up the donut example again, where are we? Hello, donut. So this donut example has a torus with a material, and you can interact with it a bit with the camera. Now, to make that work in Qt3D is absolutely trivial. Where are we gone? Keyboard handler. So basically we have our entity that represents our donut that we saw earlier on the slides. To make a camera, we literally say we have a camera. And then for the interaction with that camera, we just hook up this controller. Yep. If you were doing that in raw OpenGL, you need to worry about taking care of all the view transformations, the perspective transformation, or the model space transformations and everything yourself. Yep. So this is, the idea is it saves you writing several thousand lines of boilerplate code. Okay, but you can still wrap up your own custom shaders and materials and specify your own custom geometry very easily. Okay?
Continue her question. So your Qt3D is kind of make a higher level interface.
Exactly.
So is it still possible to use raw OpenGL commands in your framework?
At this moment, no. We don't expose the OpenGL context at the moment. That may change in the future. You can get hold of the context by providing your own context into Qt3D. And that's exactly what we do with the Scene 3D item that wraps up a Qt3D scene to show it in a Qt Quick 2 world. So if you look at the implementation of the Scene 3D custom item, you can feed it your own context, and then Qt3D will use that context to do its rendering. So you can do it that way.
Okay, thanks.
But we don't let people just issue random GL commands in the middle of the Qt3D rendering.
Hey, if you would want to implement a global like ray trace kind of model for objects to interact with each other in the scene, how would you go about to like approach the iterative term like part of such an algorithm in the shader parallel way?
This is not a ray tracer. OpenGL is a raster-based graphic system.
Yeah, so you don't have any like ideas of how it would be possible to implement.
Well,
such
you can implement ray tracers in the fragment shader or in compute shaders, but at the moment we're not worrying too much about that.
Okay, thanks.
Unfortunately, that's all the time we have.
Come grab me afterwards.
Perfect. All right.
Okay,
Thank you.
Thank you.